activity establishes basic communication by having the Arduino continuously send a simple text message like "Hello student" to the serial monitor on the computer. This activity moves into sensor monitoring by reading analog input from a temperature sensor and then converting that raw reading into a temperature value in degrees Celsius, which is then printed to the serial monitor every second. In this activity, the program shows a message when you press a button connected to the Arduino. In this activity, when you type 1 or 0 into the serial monitor, the LED will turn on or off. This activity reads values from the light sensor and displays how bright or dark the area is in the serial monitor. This project uses the ultrasonic sensor to measure the distance from the sensor to a nearby object that is displayed in the serial monitor. This project uses an ultrasonic sensor to measure the distance to an object and displays the result on a LCD. This activity uses the ultrasonic sensor to detect nearby objects. If an object comes within a set distance, an LED will light up, simulating a proximity alert system. This project is a parking assistance system that uses an ultrasonic sensor with LEDs and a buzzer to show distance. Green for safe, yellow for caution, and red with sound for danger. In this activity, an infrared sensor is used to detect the difference between a black surface and a white surface.
This activity uses the IR proximity sensor to act as a digital counter. Each time an object passes in the front of the sensor, a counter variable in the code is increased by 1. To prevent multiple counts for a single object, the code utilizes a logic flag to only increment the count once per distinct detection event. The running total is then displayed on an LCD screen.
In this activity, an IR proximity sensor module is used to count how many times an object passes in front of the sensor.
In this activity, a DC motor is controlled using a push button and an N-channel MOSFET connected to an Arduino. The MOSFET acts as an electronic switch that allows the Arduino to safely control the higher current needed by the motor. When the button is pressed, the MOSFET turns on and the motor starts spinning. When released, it turns off. Application of this activity include automatic doors where pressing a button activates a motor to open or close. This activity enhances the former one by adding a potentiometer to control motor speed instead of just turning it on or off. The Arduino reads the analog voltage from the potentiometer and uses pulse width modulation to vary how much power the motor receives through the MOSFET. Rotating the potentiometer changes the motor speed smoothly from slow to fast. Applications of this activity include electric fans, where fan speed can be adjusted with a knob, and RC car speed control. In this activity, we use an H-bridge to simply turn a DC motor on and off repeatedly. The motor runs for 1 second, then stops for 1 second in the loop. Application of this activity include basic automation system like turning fans or pumps on or off. It uses pulse width modulation to vary the motor speed. Instead of just a simple on or off, the Arduino sends a series of rapid pulses, changing how the motor receives voltage. This controls how fast it spins. Application of this activity include electric vehicle speed control. We expand control on the former activity by changing the direction of rotation using two control pins on the H bridge. By switching the polarity of the current going to the motor, it can spin clockwise or counterclockwise. Application of this activity include conveyor belt system with reversible belts. We now use two push buttons to manually control the motor's direction, one for forward, one for reverse. If no button is pressed, the motor stops. An example application of this activity is joystick or button-based control for model cars or fans. This activity combines everything from the former activities. Two push buttons control direction, a potentiometer controls speed using analog input and PWM output. Together, they allow full manual control of a DC motor's behavior, both speed and direction. This can be applied in robotic arms in vehicles and RC cars, throttle plus direction control. Through the endeavors we have undergone, we learned the fundamental principles of motor control, sensor integration, and microcontroller programming using Arduino. The experiments with MOSFETs and H-bridges taught us how to control a DC motor's power, speed, and direction through digital signals and pulse width modulation. By incorporating push buttons and potentiometers, we also explored how inputs can adjust a motor movement in real time, skills that are essential in robotics and automation. The lessons involving the serial monitor also enhance understanding of serial communication, data monitoring, and debugging, allowing learners to observe and control their circuits interactively. Activities using ultrasonic and infrared sensors also introduce concepts of distance measurement, obstacle detection, and object counting, demonstrating how sensors enable intelligent responsive systems. Overall, these activities develop the students' practical skills in circuit design, programming logic, and system integration, forming a strong foundation for building automated and robotic systems. And now, as we are nearing the end of our second quarter on robotics, we are anticipating what is yet to come and is excited to try new components like the RFID reader module and real-time clock module, as they would introduce numerous fun and interesting activities that we would certainly enjoy.